Right now, you are floating in something colder than anything you have ever felt. Not winter, not ice, not even the coldest place on earth. Something far beyond that. A place so cold, your mind can't truly imagine it. And yet, here's the question that almost no one asks. If space is that cold, why wouldn't you freeze instantly the moment you enter it? And even stranger, why do astronauts worry about overheating at the same time? How can something be freezing and burning at once? That doesn't make sense. But the truth is, it was never supposed to, because everything you think you know about cold breaks the moment you leave Earth. We grow up believing space is simple. Empty, dark, cold, a giant freezer surrounding the universe. It feels obvious. Too obvious to question. But that idea is completely wrong. Space is not cold in the way you think. In fact, in a very real sense, space doesn't even have a temperature. That sounds impossible, because temperature feels like something everything must have. Your body has it, the air has it, even objects sitting still have it. So how can space not? To understand that, we need to let go of something very familiar, something so basic. You've probably never questioned it. What cold really is. Think about the last time you felt cold. Maybe stepping outside at night, maybe touching something metal, that sharp feeling on your skin. It feels like cold is attacking you, like it's something moving into your body. But that's not what's happening. Cold is not a thing. It doesn't exist on its own. Cold is simply what happens when heat leaves you. That's it. Nothing more. The air doesn't give you cold. It takes your warmth away. Every second, invisible particles in the air crash into your skin. Trillions of them. Each one stealing a tiny bit of your heat. Your brain detects that loss and calls it cold. Now imagine something very different. No air, no particles, no collisions, nothing touching you at all. Just emptiness. So now ask yourself something strange. How can you feel cold if nothing is there to touch you? In space, that entire process disappears. There is no air pulling heat away from you, no constant collisions, no invisible storm of particles. In fact, in deep space, there may be almost nothing at all, sometimes just a single atom in a space the size of your hand. Compare that to Earth, where that same space is packed with unimaginable numbers of particles, moving, colliding, exchanging energy. In space, it's almost silent, which leads to something unexpected. If space cannot easily take your heat away, then why do we call it freezing? And here's the part that makes it even stranger. If nothing is cooling you down, what actually happens to your body's heat? Where does it go? The answer changes everything. Because temperature is not what we think it is. At its core, temperature is just motion. The faster tiny particles move, the hotter something is. The slower they move, the colder it becomes. That's all temperature really measures. Motion, energy, activity. But now imagine a place where there are almost no particles, no motion to measure, no collisions to observe, no system exchanging energy. In that environment, temperature stops behaving normally. It becomes almost meaningless. A thermometer floating in deep space would not measure space. It would measure itself, its own energy, its own heat. Because space isn't telling it anything. There is nothing there to interact with, nothing to define hot or cold in the usual way. So now we have a deeper mystery. If space itself doesn't define temperature, then what does? And why do scientists say space is incredibly cold? Where does that number even come from? to answer that, we need to understand the only way heat can survive in emptiness. On Earth, heat moves in three ways: through touch, through moving air, and through radiation. But in space, two of those vanish completely. There is nothing to touch you, no air to move around you, no fluid carrying heat. Only one path remains: radiation. And radiation is very different. It doesn't need matter. It doesn't need contact. It travels as pure energy, as light. Right now, your body is glowing, not in a way you can see, but in infrared. You are constantly sending energy outward, slowly losing heat into your surroundings. On Earth, that heat doesn't go far. The air catches it, traps it, returns some of it back. But in space, there is nothing to stop it. Your heat simply leaves and keeps going forever, which creates a very strange truth. Space is not trying to freeze you. It's not attacking you. It's not pulling heat out of your body. It's doing something much more unsettling. It's ignoring you completely. There is no environment balancing your temperature, no system stabilizing you, no hidden force keeping things comfortable. You are alone. And your heat is slowly drifting away into nothing. And yet, this still doesn't explain something critical. If heat leaves you slowly in space, then why do objects out there become so incredibly cold? Why do temperatures drop so close to absolute zero? And here's the part that feels almost impossible. How can the same object have one side hotter than boiling water, while the other side freezes solid at the exact same time? That shouldn't happen, but it does. And the reason has nothing to do with emptiness. It has to do with something almost invisible, something ancient, something that has been quietly filling the universe since the beginning of time. A faint glow, so weak you would never feel it, but so powerful. It sets the baseline for everything. And once you understand where that glow comes from, you realize something much bigger. You are not just learning about space. You are looking at the leftover heat from the moment the universe was born. And that raises a new question. If that ancient heat is still here, why hasn't it disappeared? And what happens when it finally does? Before we go deeper, if this just changed the way you see something as simple as cold, take a moment to like the video and subscribe, because what comes next is where the universe starts to reveal its real secrets. There is a faint glow filling the entire universe. You can't see it with your eyes. You can't feel it on your skin. And yet, it is everywhere. Right now, it is passing through your body, through your walls, through your planet, silently, constantly, without pause. And here's the strange part. This invisible glow has a temperature, about 3 degrees above absolute zero. Not because space itself is cold, but because something ancient is still whispering through it. Something left over from the very beginning. So now the question becomes deeper. If the universe started in a state of unimaginable heat, why is anything cold at all? Why didn't that heat just stay forever? To understand that, we have to go back. Not millions of years, not billions, but all the way back to the moment everything began. The universe was not always cold. In fact, it began as the hottest thing that has ever existed. There was no space as we know it, no stars, no planets, no atoms, only energy, dense, compressed, and unimaginably hot. Temperature so extreme that even the idea of matter could not exist. Everything was pure radiation, pure motion, pure chaos. And then it expanded. Not like an explosion in space, but an expansion of space itself. Everywhere. At once. And as space expanded, something subtle but powerful began to happen. The energy started to spread out. And when energy spreads out, it cools down, just like a drop of ink dissolving in water. At first, it is concentrated, dark, intense, localized. But as it spreads, it fades, becomes lighter, thinner, less powerful. That's what happened to the universe. It didn't suddenly become cold. It slowly cooled over billions of years. But here's the key detail. The heat never disappeared. It just stretched, weakened, diluted across the expanding space. And that ancient heat is still here today. That faint glow filling the universe is the leftover radiation from that original fire. It's like an echo, a fossil, a memory of the beginning. Scientists call it the cosmic background radiation. But you don't need the name to understand the idea. Just imagine this. You light a fire in a dark room. At first, it burns bright and intense. You can feel the heat strongly, but as the fire dies down, the room doesn't instantly become cold. There's still warmth lingering in the air, faint, subtle, but present. Now stretch that idea across the entire universe. That lingering warmth never fully disappeared. It just became incredibly weak, so weak that today it sits just above absolute zero. And that brings us back to the mystery. If this faint heat is everywhere, then why is space still so cold? Why doesn't this ancient glow warm everything up? The answer lies in how energy moves and how little there is to carry it. That background radiation is incredibly weak. Each tiny bit of energy is stretched across vast distances. It barely interacts with anything. It's like standing in a massive room with a candle at the far end. Yes, there is light. Yes, there is heat. But it's so faint. You barely notice it. And now imagine that room growing larger every second. The candle doesn't get brighter. It just gets more and more distant, more diluted, more spread out. That's the universe, expanding, continuously, forever. And as it expands, that ancient heat keeps stretching, getting weaker, colder, but never truly gone. Which leads to a haunting thought. The universe is still cooling. Right now, as you listen to this, space is getting colder. Very slowly, almost imperceptibly, but relentlessly. And that raises a question most people never consider. If the universe keeps cooling, what happens in the end? Will everything eventually reach absolute zero? Will all motion stop? Will time itself lose meaning? We're not answering that yet. But hold on to it. Because the answer connects to something even stranger. Something happening right now. On objects floating in space. Because even with this faint background heat, objects in space don't all share the same temperature. Far from it. In fact, they can experience extreme differences. Imagine a spacecraft drifting in orbit, one side facing the sun, the other facing deep space. The side in sunlight can heat up to over 100 degrees Celsius, hot enough to boil water, while the side in shadow can drop below negative 150 degrees, cold enough to freeze almost anything solid at the same time, on the same object. That's not just extreme. It's almost absurd. How can that happen? How can temperature split so violently in the same place? The answer reveals something critical. Space doesn't regulate temperature. It doesn't balance things out. On Earth, heat spreads, air moves, energy redistributes. Everything tends toward equilibrium. But in space, there is no equilibrium. No atmosphere to carry heat around. No system to smooth out differences. Each surface is on its own. If it absorbs energy, it heats up. If it loses energy, it cools down. No interference, no correction. Just pure physics, acting in isolation, which creates a universe of extremes, blazing heat and deep cold, existing side by side. And now we arrive at a deeper layer of the mystery. If space doesn't control temperature, then what does? What determines whether something heats up or cools down? Why does one object glow with energy, while another drifts toward absolute zero? The answer lies in something deceptively simple, something you experience every day, without noticing: light. Not just visible light, but all forms of it. Energy traveling through space, interacting with matter, deciding its fate. And this is where things begin to shift again. Because light is not just illumination. It is the only way energy truly moves across the universe. It is the connection between hot and cold, between past and present, between the birth of the universe and this exact moment. And once you understand how light controls temperature, you begin to see something unexpected. Cold is not just about absence. It's about isolation. And that isolation may be the most powerful force shaping the universe. Which brings us to a new question. If everything depends on energy coming in or going out, what happens to something that receives nothing and slowly loses everything? Does it just keep getting colder forever? Or is there a limit, a boundary, something it can never cross? The answer is not as simple as it seems. And it leads directly to one of the most important numbers in physics. A number so small, it feels almost meaningless. But it defines the temperature of the entire universe, and it hides a secret about how everything will eventually end. We're getting very close to that answer now. But before we go there, you need to understand one more piece of the puzzle. Because the way objects gain and lose heat in space is not just about physics. It's about perspective, about direction, about what they face and what they don't. And once you see that clearly, you'll understand why space is not truly cold, but something far more unsettling, something far more silent, something that doesn't freeze you, doesn't burn you, but simply lets you drift until your energy fades away. And the deeper question is this: if the universe began in fire and is slowly fading into cold, where exactly are we in that story right now? And how much time is left before the last trace of warmth disappears? That answer is coming. And when it does, it changes how you see everything. There is a limit to how cold anything can become. Not just in space, not just on Earth. Anywhere. A boundary that nothing has ever crossed. And maybe nothing ever will. Absolute zero. The point where all motion stops. No vibration. No heat. No energy left to give. It sounds simple, like the coldest possible temperature. But it's not just cold. It's something far more extreme. It is the complete absence of motion itself. Now here's the strange part. Even in the deepest parts of space, even in the coldest regions we have ever measured, nothing has ever reached it. Everything stops just short. Always. No matter how empty space becomes, no matter how long something drifts alone, it never quite gets there. So the question becomes unavoidable. Why? If the universe is constantly cooling, what is stopping everything from reaching absolute zero? What invisible rule prevents it? To answer that, we need to understand something subtle. Cooling is not about losing heat instantly. It's about losing energy, step by step. And each step becomes harder than the last. Imagine this. You have a cup of hot coffee. You leave it on a table. At first, it cools quickly. You can feel the heat escaping, steam rising, energy flowing out. But as the coffee gets closer to room temperature, the cooling slows down. It becomes more gradual, more subtle. Eventually, It barely changes at all. It never truly reaches the exact temperature of the room. It only gets closer and closer forever. Now take that idea and stretch it to the scale of the universe. As something cools, it radiates energy. But the colder it becomes, the less energy it has to lose, and the less energy it radiates, which means the process slows down dramatically. So reaching absolute zero would require removing every last bit of energy, down to nothing. And that turns out to be impossible, because even the act of measuring something adds energy to it. Even the faintest radiation, the weakest interaction, prevents it from ever reaching that perfect stillness, which means absolute zero is not just difficult, it is unreachable, a limit written into the laws of physics. And that connects directly to the universe itself, because even in the emptiness of space, there is always something, that faint background radiation, that ancient glow from the beginning. It never disappears completely. It sets a floor, a minimum temperature, a quiet baseline, beneath everything, so nothing can cool below it. Not yet. But here's where things take a darker turn. That background radiation is not constant. It is fading, very slowly. As the universe expands, it stretches, loses energy, becomes weaker, colder, which means the floor itself is dropping. Over time, the entire universe is sliding closer and closer to absolute zero, not reaching it, but approaching it, forever. And that leads to a haunting idea. The future of the universe is not fire, it's silence, a slow fading, a gradual loss of energy, until everything becomes cold, still, inactive. But before we go that far, we need to come back to something more immediate, something that affects every object in space right now. Because even though absolute zero is unreachable, objects still get incredibly cold. And how they do that reveals something surprising. Cooling in space is not about surroundings. It's about exposure. Imagine two identical objects, floating side by side, one facing a star, the other facing deep space. The one facing the star absorbs energy. Light hits it, warms it, raises its temperature. The other receives nothing, no light, no energy, only emptiness. So it radiates its heat away, with nothing replacing it, and it gets colder, and colder. That's the real rule of temperature in space, not location, not environment, but what you face, what you absorb, and what you lose. Which leads to a deeper realization. Space doesn't decide your temperature. Your relationship with energy does. Whether you are exposed or isolated, connected, or alone. And that idea applies to everything. Planets, asteroids, spacecraft, even you. If you were drifting in space, your temperature would not be controlled by cold. It would be controlled by energy flow. If sunlight hits you, you warm up. If it doesn't, you cool down. Slowly, silently, with no sensation at first, no wind, no chill, just a gradual loss. And here's something even stranger. Because there is no air, your body would not feel cold immediately. There would be no biting sensation, no sharp shock, just quiet, steady cooling, almost peaceful at first, which makes space even more deceptive. It doesn't feel dangerous in the way we expect. It doesn't warn you. It doesn't attack you. It simply allows your energy to drift away until it's gone. And that brings us back to the deeper question. If everything depends on energy coming in and going out, what determines that balance? Why do some objects receive energy while others remain in darkness? Why are some parts of the universe active while others fade into silence? The answer lies in something we haven't fully explored yet: light and distance. Because energy in space doesn't spread evenly. It travels. It moves outward. It weakens with distance. The farther you are from a source, the less energy you receive, which creates structure in the universe, regions of warmth, regions of cold, zones of activity, and zones of stillness. And that structure is not random. It shapes everything. It determines where stars form, where planets stay warm, where life can exist, and where nothing ever happens. Which leads to a question that feels almost personal. Right now, on Earth, we exist in a narrow balance, not too hot, not too cold, just enough energy to sustain life. But that balance is not permanent. It depends on a star, on distance, on energy flow. So what happens when that balance changes? What happens when the energy source shifts or disappears? Does everything simply cool down? Or is there something more dramatic waiting? Something that changes not just temperature, but the fate of everything? Because the truth is, temperature is not just about heat. It's about time. It's about change. It's about how long energy can keep things moving. And when that energy fades, everything else begins to follow. Which brings us closer to one of the biggest questions of all. Not just how cold space is, but how long anything can stay warm, and whether warmth itself is only temporary. We're getting closer to that answer, but before we reach it, there's one more piece we need to understand. Something that seems simple at first, but turns out to control everything. How energy spreads, and why it never comes back the same way. Because once you see that clearly, you'll understand why the universe is not just cooling. It's running out of usable energy, and that changes the story completely. There is something even more important than temperature, something deeper, something that quietly controls everything we've been talking about. Not how much energy exists, but how that energy is arranged, because not all energy is equal. Two systems can have the same amount of energy, and yet behave completely differently. One can power motion, create structure, sustain life. The other can do nothing at all. Same energy, different outcome. So what's the difference? It comes down to one idea. Order versus disorder. Imagine this. You drop a glass on the floor, it shatters, pieces scatter everywhere. That feels normal, expected. But imagine the reverse. Shards of glass suddenly sliding together, reforming perfectly into a solid glass, and jumping back onto the table. That feels impossible, not because of energy, but because of order. The broken glass is more disordered, more spread out, more random, and once energy spreads into that kind of randomness, it doesn't naturally come back. This is the hidden rule behind everything. Energy doesn't just move, it disperses, it spreads out, it becomes less useful over time. And that brings us to a concept that quietly shapes the entire universe. Entropy. You don't need to remember the word, just remember the idea. Everything tends toward disorder. Everything moves from structured to scattered, from concentrated to diluted, from useful to unusable. And this is where temperature connects to something much bigger. Because cooling is not just about losing heat. It's about losing usable energy. Imagine a perfectly organized system. Energy flowing in clear directions, powering movement, creating change. Now imagine that same energy, spread thin, random, unfocused, still there, but no longer able to do anything meaningful. That's what's happening to the universe. Not just cooling, but losing structure, losing the ability to create, slowly, but inevitably. And this leads to a question that feels almost unsettling. If energy is still everywhere, why can't it always be used? Why does it become useless? The answer is simple, but powerful. Because once energy spreads out evenly, there is no difference left to drive change, no imbalance, no direction, no flow. And without flow, nothing happens. Think about a waterfall. Water at the top has potential. It can fall, move, generate power. But once that water reaches the bottom and everything levels out, the motion stops. The energy is still there, but it can't do anything anymore. The same is true for the universe. Right now, there are differences everywhere. Hot stars, cold space, energy flowing from one place to another. That difference is what makes everything happen. But over time, those differences fade. Heat spreads, energy evens out. And the universe slowly moves toward balance, perfect balance, which sounds peaceful, stable, complete. But it comes with a hidden cost, because perfect balance means no change, no motion, no events, no life. And that brings us to one of the most important ideas in all of physics. The universe is running down. Not in the sense of stopping suddenly, but in the sense of losing its ability to do anything interesting. Every process, every movement, every reaction pushes things slightly more toward disorder, slightly more toward balance, slightly closer to a state where nothing happens. And this connects directly to temperature, because temperature differences are what allow energy to flow. Hot to cold, high energy to low energy. That flow powers everything. But when everything reaches the same temperature, that flow disappears. No gradient, no movement, no change. And that leads to a question that feels almost impossible to ignore. What happens when the entire universe reaches that state? When everything is the same temperature? When all energy is evenly spread? When nothing is hotter or colder than anything else? The answer is something scientists call heat death. Not an explosion, not a collapse, not a dramatic ending. Just a quiet, gradual fading. Stars burn out. No new stars form. Galaxies drift apart. Light becomes weaker, colder, more stretched. Until eventually, there are no temperature differences left, no energy flows, no processes, no events, just a universe in perfect balance, silent, still, endless. But here's where things become even more interesting. We are nowhere near that point. Right now, the universe is still full of structure, full of differences, full of energy gradients. Stars are forming, planets are warming, life is emerging, which means we exist in a very special moment, a window of time where energy is still flowing, where order still exists, where change is still possible. And that raises a deeper question. How long does this window last? How long before the balance takes over? Before the universe becomes too uniform, too even, too quiet to support anything at all? We're not answering that yet, but hold on to it, because the answer connects to something even more immediate, something happening much closer to us. Because while the universe is slowly moving toward balance, local systems can still create order, temporarily, stars form, planets stabilize, life emerges. But all of that comes at a cost. Because creating order in one place means increasing disorder somewhere else. Nothing escapes the rule. Everything contributes to the overall spread. And that leads to a subtle but powerful realization. Even the most complex structures in the universe are temporary. They exist because of energy flow. And when that flow ends, so do they. Which brings us back to something simple, but profound. Temperature is not just about how hot or cold something is. It's about imbalance, difference, the ability for energy to move. And when that movement stops, temperature itself loses meaning. Because hot and cold only exist when there is a difference between them. And that difference is slowly disappearing. Which leads to one more question. If the universe is always moving toward disorder, toward balance, toward stillness, then how did anything organized ever form in the first place? How did stars, galaxies, and life emerge from that process? It feels like a contradiction, but it's not. And the answer reveals something even more fascinating. Because under the right conditions, disorder can create structure, chaos can give rise to patterns, and randomness can build complexity, which sounds impossible at first, but it happens all the time. And once you understand how, you begin to see the universe in a completely different way, not as something falling apart, but as something briefly organizing itself before fading again. And that changes the question entirely, because now it's not just about how cold space is, it's about why anything warm ever existed at all, and whether that warmth was always meant to disappear. It seems like a contradiction. The universe is moving toward disorder, toward balance, toward stillness. And yet, everywhere you look, there is structure. Stars burning, galaxies spinning, planets forming, life emerging. How can both be true at the same time? How can a universe that is slowly running down still create things that are so complex, so organized, so alive? That question sits at the heart of everything. And the answer begins with something surprisingly simple. Energy doesn't just spread out randomly. Sometimes, under the right conditions, it flows in a way that creates structure. Not permanently, but temporarily. And that temporary order is what we call reality. Imagine a river flowing downhill. At first glance, it looks chaotic. Water moving everywhere, unpredictable. But look closer. You begin to see patterns, currents forming, waves repeating, whirlpools spinning in place. These patterns are not separate from the flow. They exist because of it. They are created by energy moving through the system. Now imagine that idea, scaled up to the entire universe. Energy flowing from high to low, from hot to cold, from dense to empty, and along the way, forming structures. Stars are one of those structures. They are not permanent objects. They are processes, flows of energy, mass collapsing inward, while radiation pushes outward. A balance, a tension, a temporary state that exists because energy is still moving. The same is true for planets, for atmospheres, for oceans, for life. All of it exists because energy is passing through, not because things are stable, but because they are not. That's the key. Order doesn't come from stillness. It comes from imbalance, from gradients, from differences. And as long as those differences exist, structure can form. But here's the hidden cost. Every time order appears in one place, disorder increases somewhere else. Always. A star shines by converting dense matter into radiation. In doing so, it spreads energy outward. Increasing disorder in the universe, life exists by consuming energy, by taking in structured forms and releasing less organized forms. Heat, waste, entropy. Everything that creates order locally contributes to disorder globally, which means the existence of structure does not contradict the universe's path toward disorder. It is part of it, a temporary ripple in a larger flow. And that leads to a powerful realization. Everything you see, everything you are, exists because the universe is not in balance yet, because energy is still flowing, because differences still exist. You are not separate from this process. You are a result of it. Your body, your thoughts, your awareness, all powered by energy moving through you. Food becomes energy. Energy becomes motion. Motion becomes life. And all of it contributes to the gradual spreading of energy outward. So in a strange way, life does not resist the universe's direction. It accelerates it. Which raises a deeper question. If all structure is temporary, how long can it last? How long can stars burn? How long can planets stay warm? How long can life exist? The answer depends on one thing: energy sources. As long as there are differences, as long as there are gradients, as long as energy can flow, structure continues. But once those differences fade, so does everything built on them. Stars burn because they have fuel. Hydrogen collapsing under gravity, releasing energy through fusion. But that fuel is finite. Over time, it runs out. The star changes, expands, cools, or collapses. Eventually, it stops shining. And when stars go dark, the regions around them begin to cool, planets freeze, atmospheres collapse, energy flow slows, then stops. Multiply that across the entire universe, and you begin to see the long-term picture. Not sudden destruction, not dramatic endings, just gradual loss, light fading, heat dispersing, structure dissolving, until only the most stable forms remain. Cold remnants, black dwarfs, neutron stars, black holes, and even those are not truly permanent. Which leads to a question that feels almost impossible. What is the last thing to disappear? What is the final structure in a universe that is losing all structure? We're not there yet, but we're moving toward it. Slowly, inevitably. And that brings us back to something very close to us. Because while the far future of the universe feels distant, the same rules apply right now. On Earth, in your daily life, energy flows in. From the sun, it warms the planet, drives weather, feeds ecosystems, creates motion everywhere. Plants capture that energy, store it. Animals consume it, use it, release it. Every process, every movement, every moment of life depends on that flow. And if that flow stopped, everything would begin to fade. Not instantly, but steadily, which makes our current moment very special. We exist in a narrow window, a balance between too much energy and too little, too hot, and nothing holds together, too cold, and nothing moves. Right now, we are in between, a rare state where complexity is possible, where structure can exist, where life can emerge. But that balance is fragile. It depends on distance, on timing, on conditions that will not last forever. And that leads to a deeper realization. The universe is not designed for permanence. It is designed for transition. Everything that exists for a time, because energy is still moving, because imbalance still exists, because the universe has not yet reached equilibrium, which brings us back to the core question. If everything depends on energy flow, what happens when that flow becomes too weak, too slow, too spread out to create anything at all? Does the universe simply fade into silence? Or is there something else waiting at the end? Something unexpected, hidden in the very rules that seem so final? Because sometimes, when a system reaches its limits, it doesn't just stop, it changes. And that possibility leads to one of the most mysterious ideas in all of physics. What happens at the edge of absolute stillness, when there is almost no energy left to move anything? Can anything still happen? Or is that truly the end? We're getting closer to that answer. But before we reach it, there's one more layer to uncover. Because even in a universe heading toward stillness, there are places where the rules behave in very strange ways. Places where temperature, time, and energy stop acting the way we expect. And those places may hold the final clues. There are places in the universe where the rules start to bend, not break, but stretch, in ways that feel almost impossible. Places where temperature behaves differently, where time itself begins to distort, where energy doesn't quite follow the patterns we expect. And if you want to understand the true nature of cold, you have to go there, to the edge of physics itself, black holes. At first glance, they seem simple. Objects so dense that nothing can escape, not even light. A region where gravity overwhelms everything, pulling matter inward, endlessly. But hidden behind that simple idea is something deeply strange. Because black holes have temperature. That shouldn't make sense. Temperature requires motion, energy, radiation. But a black hole traps everything. Nothing comes out. So how can it have a temperature at all? For a long time, scientists believed they didn't. That black holes were perfectly cold, completely dark, endpoints of energy. But then something unexpected happened. A realization, a small crack in our understanding. Even in empty space, something is never truly still. On the smallest scales, space itself is active, fluctuating, changing, tiny pairs of particles appearing and disappearing constantly. You never see them. They exist for almost no time at all, but they are always there. Now imagine this happening right at the edge of a black hole, at the boundary, where gravity becomes overwhelming. One of these particle pairs appears. Normally, they vanish instantly, cancel each other out. But near a black hole, something different can happen. One particle falls in, the other escapes, and when it escapes, it carries energy with it. Slowly, over time. This creates a faint glow, a tiny release of radiation, a whisper of energy, leaking out, which means black holes are not completely black. They emit radiation. They have temperature extremely low, but not zero. And that leads to a shocking conclusion. Black holes can lose energy. They can slowly evaporate. Not quickly, not dramatically, but over immense periods of time. They shrink, bit by bit, energy escaping into the universe, which changes everything. Because black holes were once thought to be the final state, the last structure left behind, permanent, unchanging. But now, they are part of the same story. They also fade. They also lose energy. They also move toward that same quiet end. And this creates a deeper mystery. If even black holes are not permanent, then what is? What remains when even the most extreme objects disappear? To answer that, we need to think about time, not as we experience it, but on a scale far beyond anything familiar. Imagine waiting, not seconds, not years, but trillions of years. Stars have long gone dark. Galaxies have drifted apart. Planets have frozen. Everything familiar is gone. Only a few remnants remain, cold, isolated, drifting in an ever-expanding space. And among them, black holes, slowly shrinking, radiating energy, fading, until eventually even they disappear. And when that happens, the universe enters a state that is almost impossible to imagine. No stars, no light sources, no structure, only extremely low energy radiation spread thin across vast distances, and particles barely interacting, barely moving. Temperature still exists, but only as a faint trace, a shadow of what once was. And this brings us to a profound question. If energy is still there, but cannot do anything, what does that mean for reality itself? Does anything happen anymore? Or has the universe reached a kind of stillness, beyond motion? It feels like an ending, but physics suggests something more subtle. Even in this near-empty state, change never fully stops. Tiny fluctuations continue, random movements, extremely rare interactions. Given enough time, even unlikely events become possible, which leads to one of the strangest ideas ever proposed. In a universe that lasts forever, anything that can happen eventually will, no matter how unlikely, no matter how rare. Even the spontaneous formation of structure, out of randomness, a brief moment of order, emerging from chaos, then fading again. Which means, even in a universe approaching complete stillness, there may still be moments of activity, infinitesimally rare, but not impossible, and that challenges the idea of a true ending. Maybe the universe doesn't simply stop. Maybe it becomes a place where events are so rare, so spread out, that they feel like nothing, but are not truly nothing. And that brings us back to temperature, because at these extreme limits, temperature loses its everyday meaning. It is no longer something you feel, or measure in a simple way. It becomes a reflection of probability, of motion barely existing, of energy almost completely uniform, and yet never perfectly so, which means absolute zero remains out of reach, not just practically, but fundamentally. The universe approaches it forever, but never arrives, and that creates a kind of infinite horizon, a direction without an endpoint, cooling without completion. And now we return to the present, to something much more immediate. Because everything we've explored, from black holes to the end of the universe, connects back to a simple idea. Cold is not just temperature. It is the absence of interaction, the absence of energy exchange, the absence of connection. And space, more than anything else, is defined by that absence, which is why it feels so extreme, so alien, so difficult to understand. But once you see it clearly, space is not trying to freeze you. It's not trying to do anything at all. It simply allows energy to move without resistance, without interference, without return. And that changes the question completely, because now it's not about how cold space is. It's about how long anything can hold on to its warmth before letting it go, and whether anything can hold on to it forever. That answer is closer than it seems, and it begins with something surprisingly small, something happening at the level of particles, something that decides how long energy can stay in one place before it inevitably spreads out again. And once you understand that, you'll see why the universe behaves the way it does. Not just on the largest scales, but in every moment, everywhere. At the deepest level, everything comes down to something incredibly small. Not stars, not planets, not even atoms. Something more fundamental. Particles in the way they move. Because temperature, energy, and even the fate of the universe are all decided here. At the smallest scales imaginable. Imagine zooming in past your body, past cells, past molecules, down to atoms, then further into electrons, protons, neutrons, and even deeper into a world where particles don't behave like solid objects at all. They flicker, they spread out, they exist as probabilities, more than things. And this is where our intuition begins to fail. Because at this level, nothing is ever truly still. Even at extremely low temperatures, particles never completely stop moving. They can't. It's not just difficult, it's impossible. And that connects back to something we touched on earlier. Absolute zero. The idea of zero motion. Perfect stillness. But here's the twist. At the quantum level, perfect stillness cannot exist. Even in the coldest possible state, particles still have a tiny amount of motion, a residual energy, something that can never be removed. This is sometimes called zero-point energy, but you don't need the term. Just understand the idea. there is always a little bit of motion left, no matter how much you try to remove it. And that changes everything, because it means the universe can never become completely still, never completely frozen. There is always a faint whisper of activity, even at the lowest possible energy state. Now imagine this, spread across the entire universe, even in the far future, even after stars are gone. Even after black holes fade, there will still be tiny fluctuations, small movements, barely noticeable, but real. And those tiny movements can have surprising consequences. Because at the quantum level, randomness plays a role. Things don't happen in fixed ways, they happen with probabilities, which means even extremely unlikely events can happen. Given enough time, and time, on the scale of the universe, is almost unlimited. So now we arrive at a strange possibility. In a universe that has become almost completely cold, almost completely uniform, almost completely still, tiny fluctuations could still create something. Not often, not predictably, but occasionally. A particle gaining a bit more energy, a small region becoming slightly less uniform, a tiny imbalance appearing out of nowhere. And that imbalance could grow. Very slowly, very rarely, but not impossibly, which raises a question that feels almost unbelievable. Could structure reappear in a nearly dead universe? Could something like a star, or even something like life, emerge again from randomness alone? The answer is not simple, but the possibility exists, and that changes how we think about endings. Because what looks like the end may not be absolute. It may just be a state where events become so rare, so spread out, that they feel like nothing, but are not truly nothing. And this brings us back to something much closer, something you experience every moment, heat. Because even here, on Earth, in your daily life, these same rules apply. Every object around you is made of particles in motion. Your body is a system of energy flow. Heat moving in, heat moving out, balance constantly shifting. When you touch something cold, you are not touching cold. You are transferring energy, your heat, flowing into something else. When you feel warmth, it is energy entering your body. Always movement, always exchange, never stillness. And that exchange is what keeps everything alive. But here's the subtle part. That exchange is never perfectly efficient. Energy spreads, it disperses, it becomes less organized, less usable, which means every action, every movement, every moment contributes to the gradual increase of disorder. Even as you sit still, your body is radiating heat, losing energy, slowly cooling, constantly interacting with your environment. Now imagine removing that environment. No air, no contact, only radiation. That's space. And in that environment, you don't lose heat violently. You lose it quietly, gradually, almost unnoticed at first, which makes space feel deceptively calm, deceptively harmless. But over time, that slow loss becomes everything. And that connects to a deeper truth. The universe does not end in chaos. It ends in quiet, not with an explosion, but with a fading. A slow reduction of motion, a gradual loss of difference, until almost nothing happens at all. And yet, even then, something remains. Tiny fluctuations, quantum motion, barely there, but never zero, which means the universe never fully reaches stillness, never fully reaches silence. It only approaches it, forever. And that creates a kind of tension. A universe that is always moving toward stillness, but never arriving. Always cooling, but never completely cold. Always fading, but never completely gone. And now we return to one of the most important questions. If perfect stillness is impossible, if absolute zero can never be reached, then what is the true limit? What is the coldest state the universe can actually achieve? And how close are we to it right now? Because the answer is not just theoretical, it is measurable. It exists. Right now, everywhere. A faint temperature, shared across the universe. A baseline, a floor, not zero, but close. And understanding that number reveals something profound, not just about space, but about time. Because that temperature is not just a measurement of cold, it is a measurement of age, a record of how long the universe has been expanding, cooling, changing. And once you see that connection, you realize something surprising. Temperature is a clock, and the universe is still ticking. But the deeper question is this. If the universe keeps cooling, what happens when that clock slows down so much that it almost stops? Does time itself begin to lose meaning? Or does something else take its place? That answer is closer than it seems. And it leads us into one of the most fascinating ideas of all. How temperature and time are connected in ways we rarely notice. And why the coldest parts of the universe may also be the closest to timelessness. There is a quiet connection between temperature and time. Not obvious. Not something you feel directly. But once you see it, it changes how you understand the universe. Because temperature is not just about heat. It is about how fast things happen. Think about this. When something is hot, particles move quickly. Collisions happen constantly. Reactions occur faster. Everything feels active, alive. Now imagine something very cold. Particles slow down. Interactions become rare. Changes take longer. Everything feels almost frozen. So in a very real sense, temperature controls the speed of reality. Hot systems evolve quickly. Cold systems evolve slowly. And as the universe cools, everything begins to slow down. Not just motion, not just energy, but change itself. Now take that idea and stretch it to the extreme. Imagine a region of space so cold that almost no interactions happen at all. Particles barely move, energy barely flows. Events become incredibly rare, so rare that from the outside, it almost looks like nothing is happening. And that leads to a strange thought. If nothing changes, how do you even measure time? Time, as we experience it, is tied to change. We notice time passing because things happen. Clocks tick, hearts beat, light moves. But if all of that slows down, if events become rare, then time itself begins to lose meaning. Not because it stops, but because nothing marks its passage. This is one of the deepest connections in physics. Time is not just a background. It is linked to motion, to energy, to change. And as the universe cools, that connection becomes more visible. In the early universe, everything was hot, dense, active. Change happened rapidly. Particles collided constantly. New structures formed quickly. Time, in a sense, was fast. But as the universe expanded and cooled, everything slowed down. Stars take billions of years to evolve. Galaxies drift slowly apart. Processes stretch across unimaginable timescales. And in the far future, that trend continues. Events become rarer, slower, more spread out, until eventually the universe reaches a state where almost nothing happens. Not because time stopped, but because change became nearly impossible. And that raises a question that feels almost philosophical. If nothing happens, does time still matter? Or does it become something abstract, something that exists but has no effect? We're not answering that yet. But hold on to it, because it connects to something even more surprising. Temperature doesn't just affect time. It also affects how we perceive reality itself. Imagine two observers, one in a warm, active environment, the other in an extremely cold, quiet region. The first sees constant motion, events unfolding rapidly. The second sees almost nothing, long stretches of stillness, rare changes. From their perspectives, the universe feels completely different, even though the laws of physics are the same. And this leads to a subtle realization. Reality is not just defined by what exists, but by how often things happen, by how quickly change occurs. And temperature plays a key role in that. Now let's bring this closer, back to something you can imagine more clearly. Think about freezing something. Water turning into ice. At higher temperatures, molecules move freely, sliding past each other, flowing. But as temperature drops, that motion slows, until eventually the molecules lock into place. Structure becomes rigid, movement becomes limited, and change becomes harder. That's a small example of a much larger principle. As systems lose energy, they lose flexibility. They lose the ability to rearrange, to adapt, to evolve, and in the extreme limit, they become almost static. Now scale that up to the entire universe. As energy spreads out, as temperature drops, the universe loses its ability to change, not instantly, but gradually, step by step, until only the simplest processes remain, and even those become rare. Which brings us back to something we've been circling around. The future of the universe is not just cold. It is slow, extremely slow, so slow that from any practical perspective, it feels like stillness. But here's the twist. Even in that near still state, time does not stop. It keeps going, silently, relentlessly, which creates a strange contrast. A universe where time continues, but almost nothing happens. And that leads to one of the most intriguing questions of all. If time continues forever, but events become infinitely rare, what does that mean for existence? Is a universe with no change still meaningful, or does meaning itself require motion, require difference, require energy flow? We don't have a final answer, but we can explore the implications. Because even now, in the present, we see hints of this connection. Cold regions of space, where star formation is slowed, where energy is scarce, where activity is minimal. These are glimpses of the future, early stages of what the universe is becoming. And yet, even in those regions, something still happens. Occasionally, slowly, enough to remind us that the process is not complete, not yet. And that brings us to a turning point. Because everything we've explored so far, temperature, energy, entropy, time, all point in one direction. A universe moving toward simplicity, toward uniformity, toward stillness. But there is one force that seems to push in the opposite direction. One force that creates structure, that pulls matter together, that builds complexity, even as everything else tries to spread it out. Gravity. And gravity changes the story, because while energy spreads outward, gravity pulls inward. While entropy increases, gravity creates pockets of order. Stars, galaxies, clusters, and that tension between spreading and gathering, between cooling and collapsing, is what shapes the universe we see. Which leads to a new question. If gravity can create structure, even in a cooling universe, how far can it go? Can it delay the inevitable? Can it create new forms of order? even as everything else fades? Or is it just a temporary resistance, a brief counterforce in a much larger trend? Because if gravity eventually loses, then everything we've described becomes unavoidable. But if it doesn't, then the future of the universe might be very different from what we expect. And that possibility opens the door to something even more fascinating, because the interplay between gravity and temperature may hold the key to understanding not just the fate of the universe, but why anything exists at all. And once we follow that thread, we begin to see that cold space is not just an empty backdrop. It is an active player in a much deeper story. There is a quiet battle happening in the universe. You can't see it. You can't feel it. But it shapes everything. On one side, energy spreads. Heat flows outward. Differences fade. Everything moves toward balance. On the other side, gravity pulls inward. Matter gathers. Structures form. Order appears. These two forces are always in tension, always competing. And the universe we see exists because neither has completely won. Not yet. Imagine this. A vast cloud of gas drifting in space, cold, thin, almost invisible. Left alone, it would simply spread out, become even thinner, even colder, fade into the background. That's what entropy pushes it to do. But gravity changes the story. Even a tiny imbalance, a slightly denser region, begins to pull in more matter. Slowly at first, then faster. As more mass gathers, gravity strengthens, pulling even more material inward. The cloud begins to collapse. And something remarkable happens. As it collapses, it heats up. That might seem strange at first. How does something become hotter? By falling inward? But think about energy. As particles move closer together, they gain kinetic energy. They move faster. They collide more often. The system becomes more active. Temperature rises. So gravity, which seems like a force of compression, actually creates heat. It transforms structure into energy. And if the collapse continues, something incredible forms. A star, a region where matter is so dense, so energetic, that nuclear reactions begin. Light is produced. Heat radiates outward. A new source of energy is born, all from a cloud that was once cold and diffuse. This is the paradox. Gravity creates order by increasing energy concentration, while entropy spreads energy, creating disorder. Both are happening at the same time, and together they shape the universe. But here's the deeper insight. Gravity doesn't break the rules of entropy. It works within them. When a star forms, it creates a highly ordered structure. But in doing so, it releases enormous amounts of energy into space. Light, heat, radiation. The energy spreads outward, increasing the total disorder of the universe. So even as order appears locally, disorder increases globally, always. No exceptions. And that leads to a powerful realization. The universe allows complexity, but only temporarily, only as part of a larger process of spreading energy. Stars shine because they are burning through their fuel, releasing energy outward, driving the universe closer to equilibrium. And when that fuel runs out, the star changes. It expands, collapses, or fades. But it does not remain as it was. Nothing does. Now imagine this happening everywhere, across billions of galaxies, trillions of stars forming, shining, and dying. Each one a temporary pocket of order, each one contributing to the overall flow. Which raises a deeper question. If gravity can create structure, why doesn't it keep doing so forever? Why doesn't the universe keep forming new stars indefinitely? The answer lies in something subtle, fuel, Structure requires energy differences. Stars form from dense clouds of gas. But over time, that gas is used up, locked into stars, ejected into space, spread thin. The raw material becomes harder to gather, harder to compress, harder to ignite. So star formation slows, gradually, then dramatically, until eventually new stars become rare, then almost non-existent. And at that point, gravity begins to lose its influence, not because it becomes weaker, but because there is less material for it to act on, less structure to build, less energy to concentrate, which shifts the balance. Entropy begins to dominate. Energy continues to spread. Differences continue to fade. The universe becomes more uniform, more quiet, more still. But before that happens completely, there is a long transition, a phase where remnants remain. Old stars, dead stars, black holes, cold matter drifting through space. Gravity still acts, but in a diminished way, pulling objects together occasionally, forming temporary systems, but nothing like the vibrant structures of the earlier universe, which leads to a haunting thought. We are living in the era of structure, a time when stars are abundant, when galaxies are active, when energy flows strongly. But this era is not permanent. It is a phase, a brief window in a much longer timeline. And that raises a question that feels almost personal. If you were to exist billions or trillions of years in the future, what would the universe look like? Would there be light? Would there be warmth? Or would everything be dark and cold and quiet? The answer is both simple and unsettling. Light would be rare, warmth would be scarce, and most of the universe would be empty. Not completely, but nearly. And yet, even in that state, gravity does not disappear. It still shapes motion, still influences trajectories, still governs the paths of what remains, but without energy differences, without strong flows, its ability to create new structure becomes limited. And that brings us to a deeper realization. Gravity builds, entropy dissolves. But neither is absolute. They operate together, always. And the balance between them determines what exists. Right now, that balance favors complexity, stars, planets, life. But over time, it shifts toward simplicity, toward uniformity, toward stillness. And this leads to one more question. If gravity can concentrate energy and entropy spreads it out, is there a point where gravity could win again, where matter gathers once more, creating new bursts of structure? Or is the trend one way, a gradual movement toward equilibrium with no return? Because if the universe continues expanding, then matter becomes more spread out, distances grow, interactions become rarer, and gravity has less opportunity to act, which suggests that the current era of structure may be the most active the universe will ever be. A peak, a moment of maximum complexity before the long decline. And that idea changes how we see everything, because it means the warmth we experience, the energy we rely on, the structure we observe, is not the default state of the universe. It is the exception, a temporary condition made possible by a delicate balance. And that balance is slowly shifting. Which brings us back to temperature, because temperature is the visible sign of this entire process. Hot regions, cold regions, energy flowing from one to the other. And as that flow weakens, temperature differences fade, until eventually everything approaches the same state. Not hot, not cold, just uniform. And when that happens, the story of structure comes to an end. But we are not there yet, not even close, which means there is still something to understand, something happening right now. in the space between stars, in the vast emptiness between galaxies. Because even in those regions where gravity is weak and energy is sparse, there are clues. Clues about how the universe is changing, clues about what comes next. And once you see them, you begin to understand something surprising. Cold space is not just empty, it is evolving, quietly, slowly, but inevitably. And that evolution is leading somewhere. Out there, in the vast spaces between galaxies, something subtle is happening. It doesn't look like much. No stars forming, no bright explosions, no dramatic motion. Just emptiness. Cold, dark, and quiet. But that emptiness is not static. It is changing. Slowly, relentlessly. And if you look closely enough, it tells you exactly where the universe is going. Imagine drifting far beyond any galaxy, so far that the nearest star is millions of light years away. No visible light, no warmth, just a faint glow, left over from the beginning. And in that region, temperature is incredibly low, only a few degrees above absolute zero. Almost nothing happens there. Particles are sparse. Interactions are rare. Energy is weak, but not zero, never zero. And that's the key. Even in the emptiest regions, there is still motion, still energy, still change. But here's the strange part. Those regions are growing. As the universe expands, galaxies move farther apart. Clusters drift away from each other. The space between them stretches. And that means more of the universe is becoming empty. More of it is becoming cold. More of it is becoming quiet. This is not just a local effect, it is global. The entire universe is slowly transitioning from a place filled with structure to a place dominated by emptiness. And that transition is already well underway. Right now, most of the universe is not inside galaxies. It is in the space between them, dark, cold, silent. And over time, that fraction will increase. Which raises a deeper question. If empty space is taking over, what happens to everything inside it? Galaxies don't just sit still. They are moving, pulled by gravity, pushed by that expansion. And over long time scales, their fate becomes very different from what we might expect. Some galaxies collide, merge, form larger structures, but on even larger scales, something else dominates. Expansion. The universe is not just growing, it is accelerating. Galaxies are not just drifting apart, they are moving away from each other faster and faster. And that changes everything, because it means eventually distant galaxies will move beyond our reach, not just physically far away, but unreachable in principle. Light from them will never reach us again. They will fade from view, disappear from our observable universe, one by one, until only the nearest structures remain, and even those will eventually drift apart, which leads to a haunting image, a future where observers, if any still exist, look out into the universe and see almost nothing. No distant galaxies, no cosmic background glow, just darkness. Their local region isolated, cut off from everything else. And that isolation has consequences. Because without incoming energy, systems cannot sustain themselves. They slowly lose heat, radiate energy outward, cool down, fade, which means emptiness doesn't just spread, it transforms what remains. Everything becomes more isolated, more disconnected, more dependent on its own internal energy. And once that energy runs out, there is nothing to replace it. Which brings us back to temperature. Because temperature is not just about how hot or cold something is. It's about connection, about exchange, about interaction. And as the universe expands, those interactions become rarer, weaker, more distant, until eventually most regions are effectively cut off, living in their own small pockets, with no external influence. And that changes the way systems evolve. A galaxy cut off from others cannot gain new material, cannot interact, cannot grow. It can only use what it already has. And once that is gone, it begins to fade. The same applies at every scale. Stars burn their fuel. Planets lose heat. Structures break down. Not because something destroys them, but because nothing sustains them. And this leads to a profound realization. The future of the universe is not shaped by destruction. It is shaped by separation. Things don't end because they are attacked. They end because they are alone, because energy can no longer flow into them, because they are cut off from the rest of the system. And that isolation is driven by expansion, by the stretching of space itself. Which brings us to one of the most important questions. What is causing this expansion to accelerate? Why is the universe not slowing down? Why is it not collapsing back inward? The answer lies in something we don't fully understand. A form of energy that exists everywhere, uniform, invisible, but powerful. It doesn't pull things together. It pushes them apart. On the largest scales, it dominates, driving galaxies away from each other, stretching space faster over time. This is often called dark energy. But the name doesn't explain it. It only labels it. Because we still don't know what it truly is. And that uncertainty opens up something important. Because if dark energy continues to dominate, then the future we've been describing becomes unavoidable. Expansion accelerates, isolation increases, energy becomes more diluted, structure fades. But if something about it changes, then the story could shift. The universe could behave differently, take a different path. We don't know yet. And that uncertainty is part of the mystery. But based on what we see now, the trend is clear. More expansion, more emptiness, more cold. And that leads to one final thought for this part. Cold space is not just a backdrop. It is the destination. Not a place we happen to be in, but a state the universe is moving toward. Step by step, moment by moment. And yet, we are not there yet. We are still in a time of warmth, of energy flow, of structure, which makes our moment incredibly rare. A brief window in a much longer story. And that raises a question that feels almost personal. If the universe is moving toward isolation, toward silence, toward stillness, what does that say about the nature of everything we experience right now? Is warmth just temporary? Is complexity just a phase? Or is there something deeper, something that persists, even as everything else fades? Because to answer that, we need to look not just at space, but at the fabric of reality itself. At what remains when distance grows too large, when energy becomes too thin, when time stretches toward infinity. And that is where the story becomes even more surprising. There is something even deeper than space becoming cold, something more fundamental than energy fading, something that doesn't depend on stars or galaxies or even matter itself, the fabric of reality. Because when everything else begins to disappear, when structure fades, when energy becomes thin and spread out, what remains is not emptiness. It is space itself. And space is not nothing. It has properties, behavior, structure, even when it looks completely empty. Right now, you might imagine space as a stage, a passive background, where everything happens. Stars exist in it. Galaxies move through it. Light travels across it. But space itself does nothing. That's the intuitive picture. And it feels natural. But it's not true. Space is active. It stretches. It expands. It evolves over time. And most importantly, it carries energy, even when there is nothing else present. This is one of the strangest ideas in modern physics. Empty space has energy, not from particles, not from radiation, but from the fabric itself, a kind of baseline energy that cannot be removed. And this connects directly to what we mentioned earlier, the force driving the universe to expand faster and faster. Dark energy, not something inside space, but something tied to space itself. Every region of space carries it, and as space expands, there is more of it, which means the total amount of this energy increases. Not because energy is being created from nothing, but because the definition of nothing is not what we thought. And that leads to a subtle but powerful shift in perspective. The universe is not just cooling, it is transforming from a state dominated by matter to a state dominated by space itself. At early times, matter controlled everything. Gravity pulled structures together. Stars formed, galaxies grew, energy was concentrated. But as expansion continues, matter becomes diluted, spread out, less influential. And the energy of space begins to dominate, driving expansion, increasing isolation, shaping the large-scale behavior of the universe. Which leads to a question that feels almost abstract. If space itself has energy, what happens to that energy over time? Does it change? Does it fade? Or does it remain constant, even as everything else disappears? We don't fully know. But current evidence suggests something surprising. It remains. Which means, even as stars burn out, even as matter spreads thin, even as temperature approaches its lowest limits, there is still something present. Not heat, not light, but a kind of underlying energy built into space itself. And that changes the idea of empty. Empty space is not truly empty. It is a sea, not of particles, but of potential, of underlying structure, of energy that does not behave like anything we experience directly. And this leads to one of the deepest questions of all. If space itself carries energy, could it ever change in a way that reshapes everything again? Could the universe enter a new phase, a new state, different from anything we have seen? Because if the rules governing space shift, then everything built on top of it would change as well. Temperature, time, structure, all of it depends on the properties of space. And if those properties evolve, then the future of the universe might not be as simple as a slow fade into cold. There could be transitions, events, changes we don't yet understand. But based on what we observe now, the trend is consistent. Expansion continues. Acceleration persists. Space becomes more dominant. And matter becomes less significant. Which brings us back to something very simple, but profound. Cold space is not just the absence of heat. It is the presence of something else, a quiet energy, a background reality that does not depend on stars or light. And as everything else fades, that background becomes more important, more visible in its effects, more dominant in shaping the future. And that leads to a new perspective. The universe is not just cooling toward nothing. It is evolving toward a state where space itself is the main actor, where matter is sparse, where energy is uniform, where change is minimal, but not zero, never zero. And that subtle distinction changes how we think about the end, because it suggests there may not be a final nothing, only a different kind of something, a universe that looks empty, but is still structured in ways we don't fully understand. And that brings us back to one of the earliest questions. Why is space cold? Not just in terms of temperature, but in terms of experience. Why does it feel like the absence of everything? The answer is becoming clearer. Because space does not interact with us the way matter does. It doesn't transfer heat efficiently. It doesn't create sensations. It doesn't resist. It simply allows energy to pass through. And when there is little energy left, it feels like nothing. But that nothing is not truly empty. It is a state of maximum uniformity, maximum balance, where differences are so small that they no longer drive change. And that brings us to a turning point, because everything we've explored, from temperature to entropy to gravity to expansion, all point toward the same direction, a universe moving toward simplicity, toward uniformity, toward a quiet state where almost nothing happens. But there is still one question left, one that connects everything together. If the universe is heading toward this state, how fast is it happening? Not in human terms, not in years or centuries, but in the true scale of cosmic time. How long does it take for stars to fade, for galaxies to disappear, for temperature to approach its lowest limits? Because the answer to that question reveals something surprising. Something that changes how you see not just the future, but the present. Because when you understand the timescales involved, you realize something almost unbelievable. We are living at the very beginning of the long story of cold. And everything we know is happening in just a tiny fraction of what is still to come. We tend to think in years, maybe decades, sometimes centuries, if we really stretch our imagination. But the universe does not move in years. It moves in timescales so vast, they almost stop making sense. And once you begin to see those timescales clearly, you realize something profound. Everything we call normal is happening incredibly early, almost at the beginning of the story. Right now, the universe is about 13.8 billion years old. That sounds enormous, unimaginable. But in cosmic terms, it is still young. Very young, because the processes we've been describing, the fading of stars, the cooling of space, the slow drift toward stillness, unfold over timescales that are far longer. Not billions, but trillions, quadrillions, and beyond. So let's slow down and walk through that future, step by step, because each stage reveals something important, something that changes how you see the present. First, the era we are in now, the era of stars. Galaxies are active. New stars are still forming. Energy flows strongly. Temperature differences are everywhere. This is a time of light, of structure, of motion. But even now, this era is already changing. Star formation has slowed compared to the past. There is less gas available, less raw material to create new stars. The universe is still active, but it is gradually losing its intensity. And then we move into the next phase, the era of fading stars. Trillions of years from now, most of the bright, massive stars will be gone. Only smaller stars remain. Red dwarfs burning slowly, quietly, for immense periods of time. These stars are incredibly efficient. They use their fuel carefully, which means they can last far longer than stars like our sun. But even they are not eternal. Eventually, they burn out. And when they do, the universe enters a new stage, a darker one, the era of remnants. No new stars are forming, only the remains of old ones. White dwarfs, neutron stars, black holes, cold, dense objects, drifting through space, occasionally interacting, occasionally colliding, but mostly just existing. And during this time, temperature continues to fall, not dramatically, but steadily. Energy continues to spread out. differences continue to fade, which leads to the next phase, the era of black holes. At this point, black holes dominate. They are the most massive structures left. They continue to interact, merge, grow, but slowly, even they begin to change. Because as we explored earlier, black holes are not permanent. They radiate energy, very slowly, almost imperceptibly. But over immense timescales, they lose mass, shrink, and eventually they disappear, leaving behind only radiation. And that brings us to the final stage, the era of near empty space. No stars, no planets, no black holes, only extremely low energy particles and radiation, spread thin across an ever-expanding universe. Temperature approaches its lowest possible values. Motion becomes minimal. Events become rare, and time stretches into something almost abstract. Now here's the part that changes everything. These stages are not evenly spaced. The era we are in now is incredibly short compared to what comes after. The age of stars lasts only a tiny fraction of the universe's total timeline. Most of the universe's existence will occur in those later stages. Cold, dark, quiet, which means the universe we experience is not typical. It is rare, a brief window of complexity in a much longer story of simplicity, and that leads to a powerful realization. If you could pick a random moment in the universe's lifetime, the chance of landing in a time like ours would be incredibly small. Most moments look nothing like this. No bright skies, no warm stars, no active galaxies, just silence, which raises a question that feels almost philosophical. Why are we here now? Why do we exist in this narrow window where energy is flowing, where structure exists, where complexity is possible? We don't have a final answer. But the question itself reveals something important. Our experience of the universe is shaped by timing, by being in a specific phase of a much larger process. And that process is still unfolding right now. As you listen to this, stars are forming. Stars are dying. Energy is flowing. Heat is spreading. The universe is changing, slowly but constantly. And that change is directional. From hot to cold, from dense to diffuse, from complex to simple, which brings us back to temperature, because temperature is the most visible sign of this entire evolution. In the early universe, temperature was extremely high. Everything was hot, dense, active. Over time, it cooled, structures formed, differences appeared, and now those differences are beginning to fade, but we are still in the middle, not at the beginning, not at the end, in between. And that in between is where everything interesting happens, where stars shine, where planets form, where life emerges, where questions like this can even be asked. And that leads to one final thought for this part. Cold space is not just the future. It is the dominant state of the universe. It always has been, in most places, and it always will be, in most times. We just happen to exist in a rare pocket of warmth, a temporary island, in a vast ocean of cold. And that perspective changes how you see everything, because it means warmth is not the default. It is the exception. And exceptions do not last forever. But before we move forward, there is one more question we need to face. If the universe is mostly cold, mostly empty, mostly quiet, then how did something like us emerge at all? How did complexity arise in a system that is moving toward simplicity? Because the answer to that question connects everything together. Temperature, energy, time, structure. And once you see it clearly, you realize something surprising. The same process that leads to the end is the one that made the beginning possible. It feels like a contradiction. A universe moving toward cold, toward stillness, toward simplicity, and yet somehow producing life, producing awareness, producing you. How does that happen? How does something so structured, so complex, emerge from a system that is constantly spreading out, constantly losing usable energy? The answer lies in a subtle idea. Not all disorder is the same, and not all order requires stability. Sometimes order appears because energy is flowing through a system, not despite the flow, but because of it. Imagine this. You place a pot of water on a stove. At first, nothing unusual happens. The water is still, calm. But as heat flows in, something changes. Currents begin to form. Patterns emerge. Swirling motion appears. The system becomes more complex. Not because it is stable, but because energy is passing through it. Now, imagine increasing that flow. The patterns become stronger, more defined, more dynamic. But the moment you turn off the heat, everything fades. The motion disappears. The water returns to stillness. The structure was never permanent. It existed only while energy was moving through the system. This is the key to understanding life. Life is not a static structure. It is a process, a flow, a system that maintains order by constantly exchanging energy with its surroundings. Your body is not a fixed object. It is a dynamic system. Energy flows in through food, through sunlight, and energy flows out as heat, as motion, as activity. And as long as that flow continues, your structure is maintained. Cells repair themselves. Processes continue. Order is preserved. But the moment that flow stops, everything begins to change. Structure breaks down. Energy spreads. The system returns to equilibrium, which means life exists because the universe is not in equilibrium yet, because energy is still flowing, because there are still differences, hot and cold, high energy and low energy, sources and sinks, and life exists in between, using those differences, sustaining itself through them. So in a very real sense, life is not separate from the universe's movement toward disorder. It is part of it, a temporary pattern, created by energy flowing from one place to another, which leads to a deeper realization. The same process that will eventually lead to the end is the one that makes life possible now. Entropy does not just destroy structure. It allows it to form temporarily, because without differences, without gradients, there would be no flow. And without flow, there would be no life. Which brings us back to temperature, because temperature differences are what drive everything. The sun is hot, space is cold, energy flows from one to the other. And in that flow, complex systems emerge. Planets, weather, oceans, life, all of it exists in that gradient. And that gradient is not permanent. The sun will not shine forever. Space will continue to cool. The difference will fade. And when it does, the flow will stop. But for now, it continues. Which means this moment is special. Not because it is stable, but because it is unstable in just the right way. Balance between extremes, allowing complexity to exist. Now here's the question that changes everything. If life depends on energy flow, what determines where life can exist? Why here and not everywhere? Why in certain regions and not others? The answer is not just temperature. It is the right combination of conditions. Not too hot, not too cold, enough energy to drive processes, but not so much that structure breaks apart. A narrow range, a delicate balance, and that balance exists in very few places, which means Most of the universe is not suited for life. Most of it is too cold, too empty, too uniform. Life requires contrast, difference, flow, and that is rare. Which leads to another realization. As the universe evolves, as temperature differences fade, as energy becomes more uniform, the number of places where life can exist decreases. Slowly, but inevitably. Which means we are not just living in a rare place. We are living in a rare time. A time when the conditions for complexity still exist. When energy flows strongly. When differences are still large enough to support structure. And that window will not last forever. But here's where things become even more interesting. Life does not just exist within these conditions. It responds to them, adapts, evolves, finds ways to use available energy more efficiently. Which raises a fascinating question. As the universe changes, could life change with it? Could it adapt to colder conditions? Lower energy environments? Slower processes? Could complexity persist, even as the universe moves toward stillness? The answer is not simple, but it opens the door to something profound, because it suggests that life, or something like it, might not disappear immediately. It might persist, change form, become slower, more subtle, more adapted to a colder universe, and that idea leads us into one of the most intriguing possibilities of all, a future where activity still exists, but at a completely different scale, where processes take longer, where energy is used more carefully, where time stretches, but structure remains, at least for a while. Which brings us to a new question. If life depends on energy flow, and that flow is decreasing, what is the minimum energy required to sustain complexity? How little energy can a system have and still remain active? Because the answer to that question defines the true limits of existence, not just for us, but for anything. And once you begin to explore that limit, you realize something surprising. Even in a universe that is becoming colder, quieter, and more uniform, there may still be room for something to persist, for something to continue, for something to exist long after everything we recognize has faded. And that possibility changes the story. Because now, the end is not just about disappearance. It is about transformation. And we are only beginning to understand what that might look like. How little energy is enough to keep something alive? Not in the biological sense, but in the deeper sense. How little energy can a system have and still process information, still change, still exist as something more than randomness? Because once you ask that question, you begin to see the future of the universe differently, not as a sudden ending, but as a gradual thinning of activity. Imagine turning down a dimmer switch. At first, everything is bright, clear, active, then slowly, the light fades. Details disappear. Movement becomes harder to see, but even at very low levels, something is still there, faint, quiet, but not gone. This is what the universe is doing, not switching off, but dimming. And the question becomes, how far can that dimming go before everything stops? To answer that, we need to think about something subtle, information. Because at its core, life is not just energy. It is organized information, patterns that persist over time, systems that can respond, adapt, change, and all of that requires energy. Not a lot, but not zero. There is a minimum cost to doing anything, to moving a particle, to changing a state, to storing a bit of information, and that cost is tied to temperature. The colder the environment, the less energy is available, the slower processes become. The harder it is to make changes, But here's the surprising part. As temperature drops, the energy required to process information also drops. Which means, in a colder universe, systems could, in theory, operate with less energy, slower, but more efficient, almost like a computer, running at a lower power setting, taking longer to compute, but using less energy per step. And that leads to a fascinating possibility. In the far future, as energy becomes scarce, any remaining systems might adapt by slowing down, processing less frequently, using energy more carefully, extending their existence over longer periods of time, not by resisting the cold, but by aligning with it, becoming part of it. Imagine a form of existence where a single thought takes years or centuries, where activity is so slow that from our perspective, it would look like nothing is happening. But internally, there is still structure, still process, still awareness, in some form. It's a strange idea, but it follows directly from the rules we've been exploring. Energy does not disappear instantly. It becomes diluted, sparse, which means there is still something to work with, just less of it, and spread out over longer times. Which brings us to a deeper realization. The end of the universe might not be defined by the absence of energy, but by the absence of usable energy. Energy that can be concentrated, directed, used to create change. And as that usable energy decreases, systems must adapt, become more efficient, more patient, more minimal, until eventually even that becomes impossible. But the boundary is not sharp. It is gradual, a slow transition from active to almost inactive, from complex to barely structured, from dynamic to nearly static. And that raises a question that feels almost philosophical. If a system changes so slowly that no meaningful events happen within any reasonable time frame, does it still count as existing? Or does existence itself require a certain level of activity? We don't have a clear answer. But the question reveals something important. Our idea of existence is tied to change, to motion, to time passing in a noticeable way. But the universe does not care about what is noticeable. It only follows its rules, and those rules allow for extremely slow processes, extremely low energy systems, structures that persist, not by being active, but by barely changing at all, which leads to a subtle shift in perspective. The future of the universe may not be completely empty. It may contain faint patterns, lingering structures, systems operating at the edge of possibility, barely interacting, barely evolving, but still not entirely gone. And that idea connects back to something we touched on earlier. Quantum fluctuations. Even in extremely low energy environments, there are still tiny movements, tiny uncertainties, random events, which means even in the coldest possible universe, there is still a kind of background activity, unpredictable, rare, but never zero. And that keeps the door open, not for large-scale structure, not for galaxies or stars, but for the smallest possible changes, the faintest possible processes, which means the universe never truly becomes static. It only approaches that state forever. And that infinite approach creates a kind of paradox, a universe that is always ending, but never fully ends, always fading, but never completely gone, always cooling, but never reaching absolute zero. And that brings us to one final layer of this question. If the universe never truly reaches stillness, if there is always some residual activity, then is there a limit to how long anything can persist? Or can certain patterns, certain structures, exist indefinitely, by adapting to lower and lower energy conditions? Because if the answer is yes, then the story of the universe does not end with silence. It transforms into something else, something slower, something quieter, something almost impossible to perceive, but still something. And that possibility leads us into one of the most profound questions of all, not just about the universe, but about reality itself. What does it mean to exist in a state where change is almost non-existent, where time stretches toward infinity and events become infinitely rare? Because at that limit, the distinction between something and nothing begins to blur. And once that boundary becomes unclear, we are forced to confront a deeper mystery. Maybe the universe is not just a story of energy fading. Maybe it is a story about the limits of existence itself and what happens when those limits are pushed as far as they can possibly go. At some point, the difference between something and nothing becomes hard to see, not because everything disappears, but because everything that remains barely changes, barely interacts, barely does anything at all. And that forces us to confront a question that feels almost impossible. What does it actually mean to exist? Right now, the answer feels obvious. To exist is to move, to change, to think, to interact, to leave some trace of activity. But all of those depend on one thing: energy flow. Without it, nothing changes, nothing happens, nothing evolves. And yet, as we've seen, the universe never truly reaches zero. There's always a tiny amount of motion, a faint trace of energy, a subtle fluctuation somewhere. So existence never fully disappears. It just becomes incredibly thin. Imagine a universe so old, so cold, so spread out, that a single meaningful event might take longer than the current age of the universe to occur. Not impossible, just unimaginably rare. In that kind of reality, does existence still feel real? Or does it fade into something abstract? Something that technically exists, but has no practical meaning? This is where physics begins to blur into philosophy, because the equations still work, the rules still apply, but the experience changes completely. Now consider something even stranger. If events become rare enough, then the concept of before and after starts to lose its significance. Time still exists, but without change, it becomes invisible, unmeasurable, meaningless in any practical sense. And that leads to a profound idea. Time is not just a dimension. It is a reflection of change. And without change, time becomes indistinguishable from nothing at all. Which means a universe at the edge of stillness is not just cold. It is timeless, in a very real way. Not because time has stopped, but because nothing is happening to mark its passage. And that creates a kind of silence, deeper than anything we can imagine. Not just the absence of sound, but the absence of events, the absence of difference, the absence of anything that defines reality as we know it. And yet, even in that silence, there is still something. Tiny fluctuations, random movements, barely there, but never zero, which means the universe never truly becomes nothing. It only approaches it, endlessly. And that endless approach creates a kind of horizon, a limit that can never be reached, a state that can never be completed, which leads to one of the most subtle ideas of all. The universe is not heading toward an endpoint. It is heading toward a limit, a boundary that it gets closer and closer to, but never crosses. And that boundary is defined by temperature, by energy, by the ability to create change. As those approach their minimum values, Existence itself begins to thin out, but never fully vanish. Now here's the twist. If the universe never fully reaches that limit, then, in an infinite amount of time, even the rarest events become possible. No matter how unlikely, no matter how complex, given enough time, they can happen. And that includes something extraordinary: the spontaneous emergence of structure, from randomness alone, not through gradual evolution, not through sustained energy flow, but through pure chance, a brief configuration of particles arranging themselves into something ordered, then fading again. It sounds absurd, but the math allows it. And in an infinite universe, or one that lasts forever, it becomes inevitable, which leads to one of the most unsettling ideas in all of science. In a universe that is almost completely empty, almost completely still, there could still be moments where complexity appears. Briefly, randomly, without warning, then disappears. And those moments could, in theory, include systems capable of awareness, thought, perception, even if only for an instant. It's a strange idea, uncomfortable even, but it follows from the same principles we've been exploring all along. Energy never fully stops, motion never fully disappears, probability never reaches zero, and that keeps the door open for anything that is physically possible, even in the coldest, quietest universe imaginable. And that brings us to a realization that changes everything. The end of the universe is not a clean conclusion. It is not a final moment. It is a gradual fading into a state where the distinction between something and nothing becomes almost meaningless, where existence continues, but in a form so subtle, so rare, so slow, that it challenges our very definition of reality. And now we return to where we began: cold space, the emptiness between stars, the silent backdrop of the universe. At first, it feels like nothing, a void, an absence. But now you can see it differently. It is not empty. It is the direction everything is moving toward, a state of maximum balance, maximum uniformity, where energy is still present, but no longer able to create meaningful change. And yet, even that state is not final, because the universe never truly stops, never truly settles, never truly reaches absolute stillness. It only approaches it, forever, which means the story never really ends. It just becomes quieter, slower, more subtle, until it almost disappears, but not completely. And that leads to one final question. If the universe never truly reaches an endpoint, if it continues indefinitely, approaching but never arriving, then what does that say about the nature of reality itself? Is reality something that needs an ending? Or is it something that simply continues, changing form, becoming less and less active, but never truly gone? Because once you ask that question, you realize something unexpected. The universe is not just a place, it is a process, an ongoing transition from something to almost nothing. And we are living right in the middle of it, at a moment where everything still feels real, still feels active, still feels alive, but moving quietly towards something far beyond our everyday experience. And that is where the final piece of this story begins. Because if everything we know is part of a transition, then what lies beyond it may not be an end at all, but something we have not yet learned how to see. And now, we arrive at the edge of the story. Not an ending, but the farthest point we can meaningfully imagine. A universe that has expanded beyond structure, beyond warmth, beyond everything that feels familiar. Cold, almost perfectly uniform, and nearly still. But not quite nothing. Never quite nothing. Because that final detail changes everything. If the universe truly ended, completely, absolutely, there would be nothing left to describe. No motion, no fluctuation, no possibility. But that's not what physics tells us. Instead, it points to something more subtle. A universe that keeps going. Quietly, endlessly, approaching stillness, but never fully arriving. And that means the story does not end. It transforms into something almost impossible to perceive. Imagine standing in that far future, if standing even makes sense anymore. There are no stars in the sky, no galaxies, no light, just darkness, stretching infinitely in every direction. Temperature, almost at its lowest possible value. Energy, spread so thin it barely matters. Time, passing, but with nothing to mark it. From any human perspective, it would feel like nothing exists. And yet, deep within that silence, the rules are still there. Quantum fluctuations still flicker. Tiny uncertainties still ripple through space. And those ripples, no matter how small, no matter how rare, mean one thing. Possibility never disappears. Even at the edge of everything, there is still a chance, however small, for something to happen. And that changes how we see the universe. Because instead of a story that ends, it becomes a story that fades, but never fully closes. A process that continues indefinitely, becoming slower, quieter, less eventful, but never truly stopping. And that leads to a realization that feels almost paradoxical. The universe is both ending and not ending at the same time. Ending in terms of structure, of energy flow, of meaningful events, but not ending in terms of existence, of possibility, of the underlying rules that allow something to happen eventually. And that brings us back to the present, to this moment. Because everything we've explored, the cooling of space, the fading of stars, the stretching of time, the thinning of energy, all of it is happening right now. Slowly, silently, but constantly. And yet, right here, right now, the universe is still alive with activity. Stars are burning, planets are warm, energy is flowing, life is thinking. You are here, aware, listening, which means you exist in one of the rarest moments imaginable. A moment where the universe is not too hot, not too cold, but balanced in just the right way to allow complexity, to allow awareness, to allow questions like this to even be asked. And that realization changes the perspective completely. Because instead of seeing the future as something distant, something abstract, you begin to see the present as something incredibly special. Not permanent, not guaranteed, but rare. A brief window in an almost infinite timeline, where everything aligns just enough for something extraordinary to exist. And that something is not just stars, not just galaxies. It's understanding. The ability of the universe to observe itself, to ask questions about its own nature, to wonder why it is the way it is. And that might be the most remarkable thing of all. Because in a universe moving towards silence, there are moments where it becomes aware, moments where it reflects, moments where it tries to understand itself before the long quiet continues. And maybe that's what this is. Not just a story about cold space, but a story about perspective, about seeing the universe not as a static place, but as a process, a flow, a transition from something to almost nothing, and realizing that we are part of that transition, right in the middle of it, Not at the beginning, not at the end, but at a point where everything still matters. Still moves. Still exists in a way we can experience. And that leads to one final thought. If the universe is gradually losing its ability to create structure, if warmth is temporary, if energy flow will eventually fade, then every moment of complexity, every instance of awareness, every experience becomes incredibly meaningful. Not because it lasts forever, but because it doesn't. Because it exists in a narrow window that will one day close. And that doesn't make it insignificant. It makes it rare. Now, before we fade back into the quiet of space, there's something I want you to think about. If this journey changed the way you see the universe, even just a little, then hold on to that curiosity. Because the deeper you look, the more the universe reveals. And if you've made it this far, you're already part of that exploration. So if you want to keep going, to dive deeper into the mysteries of time, energy, and existence, you can stay here with me. There's always another layer, another question, another perspective waiting, and maybe the next mystery is even more surprising, because if the universe can move from something to almost nothing, then the next question becomes unavoidable. What came before everything? And could it all begin again?